Standard physics describes a black hole as a one-way trip to oblivion. Once matter crosses the event horizon, the outer threshold where the gravitational pull exceeds the speed of light, it is effectively erased from the observable universe. At the center of this void lies the singularity. This is a point of infinite density, where the curvature of space-time becomes so extreme that our mathematical models of reality simply stop working. This description of a singular, infinitely dense point also serves as the foundation for the Big Bang. Our current understanding of the early universe begins with all energy and matter packed into a nearly identical state 13.8 billion years ago. This chart compares the core equations for both events. The mathematical structures describing the heart of a black hole and the first microsecond of the Big Bang are identical. General relativity treats this as a coincidence. Most cosmologists view the identical math as a sign that our current theories are incomplete, an interesting glitch that will eventually be solved by a more advanced understanding of gravity. However, some physicists suggest the math is not failing, but telling us something literal. If the equations for the birth of a universe and the interior of a black hole are the same, they likely describe the same physical event. We see this process begin when a massive star exhausts its nuclear fuel. Without the outward pressure of fusion, the star's gravity causes it to collapse inward on itself. To find this boundary, we use the Schwarzschild radius, determining the event horizon size based solely on mass. Light hitting this line is pulled inward, making the interior invisible. The equation is scalable. As we add mass, the radius expands proportionally. This raises a question of scale. We can take this local rule of stellar collapse and apply it to the largest known value in science, the total mass we can see. Testing the Schwarzschild equation against the cosmos provides a definitive check on our position in space. The result either identifies a massive flaw in the math, or it changes our understanding of the universe's physical geometry. Moving past individual galaxies, we reach the edge of the observable universe. This is a sphere approximately 46 billion light-years of radius, containing all the matter that has had time to send light to our telescopes. When we plug the estimated total mass of all stars, gas, and dark matter within that sphere into the Schwarzschild equation, the resulting event horizon exactly matches the measured radius of our universe. From an external perspective, gravity inside this radius should crush everything into a central point. Yet, Einstein's field equations show that the extreme warping of spacetime inside an event horizon causes the interior dimensions to expand. This mathematical inversion produces the same outward expansion we observe when we look at distant galaxies. The Big Bang appears to be the moment a star collapsed in a higher dimensional parent universe. That collapse triggered an inflation of space inside, creating the bubble we live in today. The alignment between the Schwarzschild radius and the size of our observable universe suggests we are currently existing inside an event horizon. This recontextualizes the black holes we observe in our own night sky. Each one functions as a seed for a new volume of spacetime. This process is known as cosmological natural selection. Every stellar collapse in our universe spawns a new, expanding baby universe on its interior, which eventually produces its own stars and its own black holes. This framework replaces the image of a dying, lonely cosmos with a cycle of continuous reproduction. Reality behaves less like a clock winding down and more like a biological system expanding through an infinite lineage. The dark patches of the night sky are the inner walls of a cosmic womb. We are part of a vast genealogy of universes, each one nested